Welcome to the fascinating world of quantum computing. I know, the second you hear the word quantum, it instantly sounds like science fiction, right? Like something out of a futuristic movie. But in this explanator, we're going to completely demystify it. We're going to take all those highly abstract ideas and ground them into concrete, real-world physics rules. Basically, we're going to fundamentally rethink how information is processed at the absolute smallest levels of reality. By the time we're done here, you won't just understand the hype, you'll actually understand the underlying mechanics. And most importantly, you're going to be fully equipped to completely ace your exam on this subject.
Okay, so here's our game plan for this explainer. We're breaking down this potentially intimidating topic into bite-sized, totally logical chapters. We'll start with the core mechanics, move right into the math foundations, explore the landmark algorithms that make all of this so powerful, and finally, we'll wrap the whole thing up with a rapid-fire exam cheat sheet. Let's get into it. Kicking things off with Chapter 1, Core Quantum Mechanics. To truly grasp quantum computing, we really have to throw out our old assumptions and rethink how a computer processes information from the ground up, using the incredibly strange laws of quantum physics.
So in a classical computer, everything runs on bits. You probably know this. A bit is strictly either a 0 or a 1. It's like a coin lying flat on a table. It's heads or it's tails. End of story. And if you want to test 4 different inputs, you literally have to run the computer 4 separate times, sequentially. But a quantum computer uses qubits, or quantum bits. Because of this mind-bending physical property called superposition, a qubit can exist in a state that represents both 0 and 1 at the exact same time. So instead of that flat coin, imagine a coin spinning rapidly in midair. It's this blur of both states simultaneously until it finally lands. That right there, that spinning coin, is exactly what a qubit is doing.
Now that spinning state of superposition leads us directly to our next absolutely vital concept, quantum parallelism. Think about what this actually means for raw processing power. Imagine having to navigate a massive, complex maze. Classically, you'd have to walk down every single dead end, one by one, back up, and try again until you finally find the exit. That's classical computing. Now imagine being able to walk down every possible path at the exact same instant. Boom. That is the incredible power of quantum parallelism. It's the physical mechanism that allows a quantum computer to evaluate a function for a massive number of inputs simultaneously in just one single computational step. It isn't just fast, it's literally processing all those superpositioned answers concurrently.
The crucial mathematical key here, and you'll want to remember this, is 2 to the power of n. See, in the classical computing world, adding more bits just gives you a few more data slots. It's a very steady, linear, kind of boring progression. But with quantum computing, because of superposition, every single time you add just 1 qubit, you double the entire system's power. If you have n qubits, your computational workspace grows exponentially to 2 to the power of n states simultaneously. To put that into perspective, just 50 qubits gives you over a quadrillion states. A quadrillion! It's this massive exponential explosion of processing potential that classical systems literally cannot replicate.
Well, okay, hold on. There is a major catch here. If the computer calculates everything at once, why can't we just read all the answers, right? Well, the moment you observe or measure a quantum system, that spinning coin stops. It collapses into just one random answer. To solve this, we rely on interference. Quantum states act a lot like ripples or waves in a pond. When waves meet, they interact. Through constructive interference, we can perfectly align the peaks of these waves to amplify the probability of the correct answer. Think of it like a choir singing in perfect harmony. It gets louder. And through destructive interference, we deliberately make the waves cancel each other out to eliminate the incorrect answers. It's exactly the same physics used in your noise-canceling headphones, creating an anti-wave to silence background noise. The entire goal of a quantum algorithm is to carefully manipulate these waves until the wrong answers go totally quiet, giving you a 100% chance of measuring the right answer when that coin finally drops.
And driving all of this incredible wave manipulation is entanglement. Entanglement is a uniquely quantum phenomenon, where 2 or more qubits become so deeply connected that the physical state of one instantly dictates the state of the other. And the crazy part? This happens regardless of distance, even if those qubits were literally light years apart. It's so bizarre that Albert Einstein famously referred to it as spooky action at a distance. But this spooky action is exactly why that exponential workspace actually functions. Entanglement allows these isolated qubits to share information instantaneously and act in perfect, unified lockstep. It is the true, invisible engine powering all these quantum speedups. All right, Moving right along to Chapter 2, the mathematical foundations. Because if we want to actually control these wild physical phenomena and build real applications, we need some highly specific mathematical rules of the road.
In standard classical computing, you control bits using logic gates. You've probably seen them as and, or, and not gates. They just flip switches on and off. But to manipulate those delicate spinning qubits, we have to use quantum gates. We transition completely away from those clunky logical operators and instead use something called unitary matrices. Try to think of unitary matrices not as rigid gates, but as smooth mathematical rotations. They gracefully shift the probabilities of our spinning qubits without forcing them to stop and collapse.
Now, I know unitary matrices sounds like scary math, but don't let it intimidate you. It's just a strict set of rules required for two absolutely fundamental reasons. First, preserving probability. A unitary operation ensures that the total probability of all possible outcomes always adds up to exactly 1, or 100%. I mean, you can't have a 110% chance of something happening in reality, right? Second, reversibility. Look, if you push data through a classical AND gate and get a 0 out, you're left completely guessing what the original inputs were. That data is just destroyed. But unitary operations are incredibly elegant because they are always uniquely reversible. You can consistently work backward from the output to uncover the exact input. You don't lose a single drop of information.
Which brings us perfectly into Chapter 3, the landmark algorithms. See, quantum computers aren't just universally faster at every single random task. You can't just plug in a standard video game and expect it to run a million times better. They need incredibly specific algorithms built to harness those unitary matrices and wave interferences to truly crush classical limitations.
First up on our tour of quantum breakthroughs is the Deutsch-Jozsa algorithm. Imagine you're handed a black box function, and you desperately need to know if it's constant, meaning it always spits out the exact same output, or if it's balanced, giving evenly split outputs. Classically, to be absolutely sure, you'd have to manually check just over half of all the possible inputs. It's incredibly tedious. But utilizing quantum parallelism and interference, the Deutsch-Jozsa algorithm solves this problem in exactly one single try. Now, while this might sound like a purely theoretical puzzle, its creation was a massive historical landmark. It was literally the very first algorithm to definitively prove that quantum computers actually could be exponentially faster than classical ones. Next up is Grover's algorithm, which tackles a much more relatable problem: searching an unsorted database. Think of it like trying to find one specific person's name in a massive, totally disorganized phone book. Classically, you have no choice but to check every single item one by one until you finally find it. Computer scientists call this linear time. But Grover's algorithm uses a really clever technique called amplitude amplification. This essentially turns up the volume on the correct answer while completely muting all the wrong ones. By doing this, it finds the target item in roughly the square root of n steps. It takes a sluggish, linear search and supercharges it into a massive quadratic speedup. A real game changer. And then, we arrive at the heavy hitter, Shor's algorithm. The core problem here is finding the prime factors of massively large whole numbers. Why on earth does that matter? Well, because this specific, incredibly difficult math problem is literally the security backbone of modern internet encryption, like RSA. Every secure email, every bank transfer, every password you have relies on this exact math being too hard to solve. For a classical computer, finding these factors takes an astronomical amount of time, often thousands of years, because the computational difficulty grows exponentially. But Shor's algorithm efficiently solves this. It uses a complex mathematical tool called the quantum Fourier transform to spot hidden patterns or periods deep within the numbers. This allows it to quickly factor the integer, representing an exponential speedup that outright shatters the absolute bedrock of classical encryption. Okay, Chapter 4. Let's dive into our final section. To fulfill our promise from the start of the explainer, we are going to deliver the ultimate rapid-fire cheat sheet so you are fully prepared for your exam. Let's lock this in. First things first, you are almost guaranteed to be asked to write out the 4 Bell states, which represent maximum entanglement between 2 qubits. But please, do not try to just memorize these formulas by brute force. Just look at the patterns. If the exam asks for a phi state, notice how the qubits inside always match. They're either 0, 0 or 1, 1. Meanwhile, if you are asked for a psi state, the qubits are always opposite, 0, 1 and 1, 0. The plus or minus simply dictates the mathematical sign between them in the equation. Remember that simple trick, and you're going to nail this question instantly. Now listen up, because here is a very common trap that students fall into, confusing the difference between quantum parallelism and quantum speedup. They are absolutely not the same thing. Parallelism is merely the mechanism. It's the physical hardware's capacity to process 2 to the power of n states simultaneously due to superposition. But parallelism alone doesn't give you the final answer, remember? Because of that measurement collapse problem we talked about earlier. Speedup is the ultimate result. It's the measurable time reduction you get only when you successfully combine that parallelism with interference to confidently extract the correct answer. Just remember, parallelism is the tool, but speedup is the goal.
Finally, keeping track of those 3 landmark algorithms and what they actually achieve is critical. So here is your ultimate one-line summary map. If a question asks about evaluating a hidden function as constant or balanced in just a single step, you point right to Deutsch-Jozsa, which delivers an exponential speedup. If your goal is to search through an entirely unsorted database quickly, you use Grover's for a quadratic speedup. But if you need to crack encryption by finding the prime factors of a massive integer, that's Shor's algorithm, netting you an exponential speedup.
And that brings us to the end of our explainer. But before we go, I want to leave you with a thought. We just saw that Shor's algorithm efficiently breaks the very mathematical security backbone of modern internet encryption. So, now that you truly understand the raw power of qubits, superposition, and quantum algorithms, what does the immediate future of cybersecurity and data privacy actually look like in a quantum world? It's a thrilling and honestly maybe slightly terrifying question to ponder. Keep learning, keep questioning, and I'll see you in the next explainer.